to be here today. My name is André Brodtkorb. I'm a professor of scientific computing, which means that I work with both mathematics and computers, sort of the intersection there. I'm also the head of the Department of Computer Science at Oslo Metropolitan University. And today I'll be showing you some volcanic eruptions and how we can try to estimate these. Not going to today, but kind of going tomorrow, making the predictions on where the ash is going. And you may ask, why is this really a relevant question? You don't hear too much about volcanoes on a day-to-day basis, but these are huge events when they happen. So back in 2010, we had the Eyjafjallajökull eruption at Iceland. And if you look at this image here, you're going to see the small farm, which is here in the scenery. You can see sort of the extent of the height of this ash plume. Now, the thing that happened was that the complete European airspace just shut down completely. And that's terrible if you're on vacation, because suddenly you're stuck on Schiphol with thousands of other people not able to go home. But that's a minor issue. It's much worse for the people who need ambulance planes and helicopters and other assistance, putting out fires with airplanes and so on. So a lot of important societal infrastructure depends on airline traffic. So we need to know where this ash is and where it's going. So I'm trying to give you today some idea of how we can answer the questions, how much ash is there? Because a little bit of ash might be okay, but too much and it's a challenge for the airline engines. Because what happens is that the volcanic ash turns to glass in the jet turbines, and then the jet turbines cease to work. And then you have a huge problem if you're in an aircraft. So you need to know how much it is, which latitude, longitude, and what altitude. Could you fly above the ash cloud or below? And also at what time? When is it safe to fly at what point? Now, the thing that we use to do this, and I'd like to mention that this is a collaboration with the Norwegian Institute of Air Research and the Norwegian Meteorological Office. So we've done this. We look at the weather forecast. And if we know the weather forecast, we know where the wind is blowing, and we can estimate where things will drift if we know where they are today. And then if we know what the exact volcanic eruption was, we can predict the future. So here you see an example. Let's say we have 0.2 tons of volcanic ash at 1,000 meters of altitude. And then we have 2.5 tons of volcanic ash at 3,000 meters altitude, and then 4.7 tons at 5,000 meters. Then we can advect that with the weather forecast and give predictions to the airlines and the relevant public actors. But it's not so simple. We need to figure out how much ash there is, because we don't know that. We could start with like an uneducated guess, having an expert thinking of a number. The problem is that we don't really have these experts readily at hand when there isn't an eruption. But then we could make more of an educated guess. We could find a similar historic eruption. We could look at on-ground deposited ash, measure the ash cloud height through these planes or radar. Or we could do ground concentrations of ash through air filters. But all of these have a time delay before you actually get it. What we can do with the satellite images is to see the whole extent of the ash cloud as visible from a satellite, which is really valuable. Now, we've been using the Slister instrument from Sentinel-3, and this instrument can more or less capture the temperature. So think of this as an advanced temperature sensor, and it gives you the view of the Earth's temperature. The very cool thing about this satellite is that it has two directions where it can view things. It can view through the nadir swath, that's the perpendicular swath down here, about 1,400 kilometers. And then it has the oblique swath. So when the satellite flies above the Earth, it will capture the same exact point on the Earth from two views. And that gives us a stereo view of a potential ash cloud. And we can, from that, deduce the altitude. So we can see if it's 3 kilometers or 7 kilometers or so on. And that's a really good benefit to increase the precision of our estimates. But this is difficult. It's really, really difficult, because what we're trying to figure out is what was emitted at the volcano originally up here that could cause what we observe with the satellite many hours later on, because the ash which has drifted on takes a lot of time before it moves on. So this is the challenge. How can we figure out the eruption that could explain what we see in the satellite's images? So in come mathematics, a very good tool that I love. And I'm not going to show you any formulas today because they're a bit too complex to grasp in 15 minutes, but I'll give you the essence. In this graphic, we have two important things. It's the satellite images. They will give us an estimate of how much ash we think we observe, and I'll come back to why we think we observe it. And then we have some potential emissions. So this unit emission simulations, those are potential eruptions. And we want to find a combination of these potential eruptions that could explain the satellite observations we have. In addition to these two input parameters, we have an initial guess, sort of to guide our mathematics into finding something which is physically plausible. Because in this mathematical framework, it could potentially say that, well, if you admit minus one ton of ash, like negative amount of ash, you could explain the satellite observations. We know this is not physically plausible, so we sort of need to limit it at some point. But if we take these three inputs here, the initial guess, the satellite observations, and all of our potential eruptions, gather them into a huge mathematical matrix, we can massage this matrix using some mathematics and come up with a better prediction of what was actually emitted. And you see, in this case, we go from an initial guess with quite a large eruption on the 14th of April around noon to something which is reduced in magnitude in terms of how much ash is emitted, but the concentration is much higher and it's much closer to ground. So here, the inversion framework helps us to say that the actual layer in which the significant ash was erupted is closer to ground than what we originally thought. All right, the unit emissions. These are potential eruptions. Now, to make the mathematics work better, we systematize it a bit. So first, we pick a time point. Let's say the 16th of April at noon. And then we run different scenarios. In scenario 1, we emit one ton of volcanic ash, 1,000 meters above ground. And that will give us an ash cloud which looks like this a couple of days later. If we do the exact same experiment, but emit the ash at 3,000 meters altitude, we will get a different scenario. So you see the ash cloud has actually moved into different places because the wind is different at 1,000 and 3,000 meters above ground. And the same, of course, with 5,000 meters. So we do this. We advect volcanic ash emitted at different time points and different altitudes to generate a huge set of different volcanic eruptions. So it's a quite complex thing to imagine, but think of this, a whole set of different possible volcanic eruptions. That's the one input we use. The other input that we use are the satellite images. And unfortunately, even though we have very good instruments, nature is not always playing nicely. So this is not as nice a photo that I showed earlier, where you see that there's a mix between the volcanic ash, which is this darker brown cloud, and the lighter clouds, which are regular clouds. Now we want to detect sort of a temperature difference here and say that, well, we think that this brown cloud here is volcanic ash. The problem is that up in the left-hand corner here, for example, this is not volcanic ash. But according to the instrument, it has a signature which looks a lot like volcanic ash. So we do get some so-called false positives, which tell us that there may be volcanic ash there in terms of our measurements. But if we look at like the image here, we see that this cannot be. And so you see also there are other places here with these green to yellow colors, which show that there may be some ash here in which we know that there is no ash. There are other things in this image. The blue ones, they show that here we know that there is zero ash. And then the white one is we don't really know. it's difficult, for example, this cloud system up here, to say whether it's ash or volcanic ash, whether it's clouds or volcanic ash. And then finally, we have some things down here where we may have some false negatives. If we look at this image, we can see that there must be an ash cloud here because we know there's an ash cloud which has reached the coast of Norway. There should be some ash here, but it may be beneath some clouds which are higher in altitude. So from our satellite, it looks as though there's zero ash here. So we do have these issues that we have to work with in the mathematics. So it's not as simple as just having the mathematical tools and then getting a perfect solution. We have to work with a lot of uncertainties. Now let me show you a video. This is a video of the eruption as viewed from the satellite. Now you can see the timing, it starts on 13th of April, so the big eruption comes a bit later. But look at that there, when you see this movie, you see that there will be no ash in the beginning. And that's because it's covered by other clouds. So yeah, now it's running. You see that there may be some traces of things that we think may be volcanic ash. You see some, maybe some false negatives here and there. And then at some point, we see the second eruption period where you see that, well, here we have some proper eruption going on, which we can model and see that it actually runs through. Okay, so that was more or less the volcanic ash detections. And you see that after at some point, it becomes difficult because there's a lot of volcanic ash in the atmosphere, just residual, just working its way around these low and high pressures. Now, I started with the saying that we had these inputs, the unit simulations or the potential volcanic eruptions, and then we had the satellite images, which give us the observations. We gather these into a so-called source receptor matrix, which tries to correlate them to say that, well, if this eruption looks a lot like what we observe, we give it a higher weight. So we end up with this kind of matrix, and this matrix is huge. So if you look at it here, this has something like 600, 700,000 lines or rows in it. It has 1,200 or so columns. So there's a huge number of measurements and simulations that we try to correlate here. By doing this and massaging this matrix, we get something like this. Now I want to just quickly explain to you what you were looking at here. On the right-hand side, we see the exact same we saw earlier. These are the satellite images, just the observations. And the bottom here, which is this panel here, shows our initial guess of how violent the eruption is. So it starts off with quite a significant eruption, a second eruption here, and then third big events over here. On the left-hand side, we're going to see our simulated results. Now, the really important thing that I want to highlight here as well is that going from these satellite images to something that you can use in an airplane or in an air traffic controller setting, you need more information. So look at the difference between the scarcity or the sparsity in the satellite images and how much we kind of fill in on the left-hand side. Finally, you're going to see three different colors. It's going to be red, it's going to be gray, and it's going to be turquoise. And these three colors correspond to the different levels of ash which are used operationally when forecasting ash to airline pilots. So here we go. You see on the left-hand side, it's a much more detailed photo or image of where the volcanic ash and potentially is. Whilst on the right-hand side, you barely see anything. You have no idea where it is. And especially when it comes to the concentrations. And then we come into the second larger eruption period. And you see that the inversion here comes up with quite good descriptions of the eruption once more. And finally, we're nearing towards the end of this kind of major volcanic event. And we see that the ash cloud also just disappears. Good. Then I want to end with a short summary. It's really important to forecast these volcanic ash clouds when there's a volcanic eruption. But it's difficult, and it really needs these satellite observations. But it also needs the forecasting capabilities to make sure that we get a more detailed view than just what the satellites can give. And the cool thing about this work is that it appears somewhat robust in terms of what results it can give compared to just having a best guess from an expert. So with that, I'd like to thank you for your attention, and I'm open for questions.
Thanks again for your presentation, André. It was really nice, and people enjoyed the little animation at the end. So thanks for that. So we'll go to the question, and the first one being, what is the function of the sea and land surface temperature radiometer mentioned in the presentation?
Good question. It's difficult to detect volcanic ash. So the SLISTER, or the sea and land surface temperature radiometer, will give a slight indication that the temperature signal from volcanic ash is different than regular clouds. So you can distinguish between regular clouds and volcanic ash. And by doing that, you can identify where you have ash, which then comes as the input to the mathematical framework.
Okay, thanks a lot for the explanation. It's clear. The next question being, which satellite data was used for the modeling?
So I think this exact one, I believe, was from the SLISTER instruments. So this is back in 2010 satellite imagery, which goes back then. But it's the details are in the paper, and the cool thing here is that the exact data which are used to produce these results are also on Zenodo, so you can download it all and run it on your own computer. And that's one thing that was kind of missing from this presentation, but one of the aims of making this framework was also to make something which is fast. Previously, this had to be run on a supercomputer with about 200 gigabytes of memory to be able to run at all. We reworked this so it runs faster, and now it runs on a regular laptop. So you can run this on your laptop computer.
Okay,
So,
okay,
yeah.
Okay, thanks a lot. So, and yeah, the paper was made available on the chat, so people can also have a look at that. Okay. Next question, when measuring a volcanic ash eruption, what other factors are typically assessed during the eruption?
Well, there are so many volcanic, I'm not a volcanologist, so I don't know the details, right? But there are so many things. Like, you don't necessarily care about how much ash is erupted, you care about how much ash remains in the atmosphere. So you want to know the fine ash fraction and these things. So detailing what happens during a volcanic eruption goes a bit beyond my expertise, but it's a lot. And it's also sometimes other gases that don't turn up on satellite images that you really care about, which you only can pick up with ground sensors, like sulfur and these things.
Okay, thanks a lot. Okay. How can your model be cross-checked with in-situ data?
Good question. How can we cross-check this with reality and make sure that we actually model something which is real and not just a fantasy? Satellite images are somewhat of satellite images give us some indication. It's difficult because what you get on ground is the fallout of the volcanic eruption. So you're not necessarily the thing that you care about. So it's difficult. You do have some volcanic eruptions where you have planes which fly through the ash cloud, and you can actually get some concentrations here and there, and those may be good. So the cross-checking here is like a qualitative assessment compared with other results of the same eruption, because this is a kind of well-studied volcanic eruption up towards the measurements that we have.
Okay. Okay, thanks a lot. This question, so does the example Jupyter notebook that has been used for this example is available to demonstrate the best use of satellite observation?
Well, I think the actual Jupyter notebook that was used to make this video is on my personal computer, but I have no problem making that available. But everything else, like making all the data available, that's just open and on Zenodo, so it's available for eternity in principle. So if there's requests to get access to it, I'd be happy to share it. There's no, yeah.
Okay, thanks a lot. I think your contact is on the slides, if I'm not mistaken, so people will
Yes.
be able to contact you. Thanks again. Okay, this kind of an open question. Can we make simulation by using the same concepts to simulate an explosion of a nuclear plant? Sorry.
Yes. So there has been this exact framework has been used also to study part of the Chernobyl incidents. So the same mathematical framework can be used, but there are differences in how the atmospheric chemistry of radioisotopes and volcanic ash are different. So you need to have different mathematical tools there. But it's possible. So the inversion procedure is definitely possible to use there. But a challenge with nuclear power plants is that you have fewer observations. With satellite images, you can see the whole area you're interested in. But with radioactive isotopes, you basically just have point measurements. And if your volcanic or if your radioactive ash cloud is just a kilometer away from your point source, you will get 0 on your point source. So it's a challenge with the observations.
Yeah. Okay, yeah, thanks. Good to know if you people want to try, but yeah. Okay. Okay, next question. Can this model be used for predicting other volcanoes in Asia or the Pacific?
Yes. So if you have this requires that you have a way of advecting the ash. So as long as you have a way of simulating the ash going forward, you can use this framework. So I don't have a setup for predicting volcanoes in Southeast Asia or the Pacific. So, but if you have that, the source code is there, and it should be relatively straightforward to actually plug in the different sources and make this run.
Okay, thanks a lot. Okay. Did you use inversion modeling here or machine learning? What is the name of this model or machine learning used here?
Yeah. So this is where the magic sauce is hidden, right? Where where you're actually doing. This is not machine learning. It's a traditional inversion, so it's based on least squares inversion. The formulation, sort of when you formulate your least squares, it has to be in some sort of basis, and the basis here is important. So it's formulated in special basis, and then you have to have the relaxation parameters to make it give physical answers, because there's nothing in least squares to make sure that it's physical. So it's essentially least squares with some add-ons to make it sure it's physical, robust and physical. Yeah.
Okay, thanks a lot for this answer. We will have time for 2 more questions. What workflow orchestrator do you use and what supercomputing service do you employ?
Okay, so I don't know what workflow orchestrator means in this context. I'm going to interpret that it means like the batch scheduler for the supercomputer. I think this was run with Slurm on the Nordic Cooperative Operational Infrastructure for Metrology. So this runs on the MetCoop infrastructure, supercomputers. This was actually run on one in Sweden. But the inversion procedure, after you've run, that's for the forward modeling, the potential volcanic eruptions. But once you have those, everything can run on your laptop.
Okay.
Yeah.
Okay, well, good to know. Also, thanks. And yes, so for the last question, a more open question, can volcanic ash contribute to climate change? If so, how?
A wonderful question. I think the definite answer is yes, it can contribute to climate change. The details of how is way beyond my knowledge, unfortunately. But I know it may have some cooling effects, but this is just from me reading things, not me as an expert.